All, good afternoon. My name is Vaibhav. I am an experimental physicist at Rheology and Light Scattering Lab here. So, I want to talk about an application of laser that is very useful in terms of tiny force measurements. So that is I want to talk about trapping tiny particles using laser. So, first, this is a picture that you all must have seen in some sci-fi movies, where this is a tractor beam where a UFO is lifting a cow. Actually, this is not a real picture, but so is it possible to do something like this? Is it possible to control movements of objects, movements of some objects using light? So, yes, it is possible, but not for large objects. We can control the movement of small particles that are quite small, micron size particle, using laser light, that is high intensity laser light. And recently in 2018, Arthur Ashkin won the Nobel Prize for developing this technique that is called optical tweezer, and it is useful for this trapping of micron size particles in using high intensity lasers. So, before going further into that, I would like to talk about some basic properties of light that are so simple that and that are the main physical processes involved in this optical tweezer process. So, one of that is the refraction of light. So what happens as light travels from one medium to another medium? So, since each medium has different refractive indexes, that is the property that is inherent of the system, inherent of the medium. So, as light goes through one medium to another medium, it changes its direction. It changes its direction, and the amount of the change in direction, that is the amount of bending, will depend on the difference in the refractive indexes of the beam. So, and the other fact is that light is made up of photon, and then since it is made up of photon, it carries momentum. So, initially we only know that light is a massless thing which does not push anything. So, but it is not true. Light in terms of particle theory, light is made up of photon, and it also carries the energy and momentum, and it can be used to push or pull something. But since the effect is quite small, and in daily life we can't comprehend that effect, that is quite small. So, it is in the range of 10 to the power minus 7 newtons. So, for comparison, if 1 kg object will exert a force on earth of 9.8 newton. So it is quite small, but so let's see. So there is a mirror. So if a light shines on it, and then it gets reflected due to the mirror is 100% reflectance, and due to this change in direction of the light, there is a change in momentum or change in momentum of the light. So since momentum should always be conserved, and then for that to happen, the mirror will also feel a force, and that force is due to this light. So light can also push things. So and this force is called this Fs, which is this radiation pressure, and I'll call it light pressure. So, and this light pressure can also exert on this spherical object, which are this transparent object, due to this refraction that I told about. So, if light is coming to this object, and it is getting refracted, and then it will pass through this object through reflection, and since the light has changed its direction, so there is this change in momentum of light, and which, since the momentum has to be conserved, so the particle will feel a force, that is, since we know Newton's second law, F is equal to dp by dt. So so the bead will feel a force, and since this bead is quite small, so the effect of the forces could be comprehended by this particle. So, and that force is going to this direction. So, if we put this same beam in front of laser, that is just a light with high power. It is a coherent beam and a high power beam, and it has this okay. So, it has this intensity variation so it is more intense in the center, and as it goes, it is less intense. So, this kind of beams are called Gaussian beams. So, if we put a bead or a transparent object in a sphere in the mid of this laser. So what will happen is that as the light will pass through it, light will refract, and then in both side light is reflected in the both side. So the total resultant force will push the particle in the front direction, and this force is the scattering force. But for this same laser, what if this the bead is not completely at the center? What if it is little off center? Then what will happen? So so in this case, the light that will go through the center, and then it will get reflected from the transparent bead. It has more intensity from the center. So what will happen is that there will be a restoring net force towards the center of the beam. And so what we are talking about, we want to trap some particle. We want to control the movement of small particles. So we want some restoring force. So if we move something, it will come back. So in this case, there will be a restoring force which will act downward. I am calling it Fg. G means gradient, which is just since it is a change in intensity. So the force is acting. A force is acting due to this change in intensity. So it is a gradient force, and at the same time there is this scattering force that I talked about earlier. But the effect of gradient force will be to put the particle at the center of the beam, so to the region of high intensity. Similarly, if the particle is off centered on the other side, then the light that is going through the center and then reflecting through this sphere, it is more from this upper side, and then there will be a restoring force which will still act upon the upside, and the beam will go at the center. So here particle will likes to be at the region of highest intensity. So since we want to trap a particle, but here only we have trapped the particle in this line, so it can't go in up or down, but there is this scattering force also that will act, and then the particle is not actually stable. So how can we make a particle stable in this case? So particle can't go in a two direction, but it can go in the other in the direction of laser beam. So one way is to just put a laser on the upper direction, and then the gravity will act, and then this scattering force will act, and both can balance. But that is quite unstable. That is not practical, because if any small disturbance will create, so that is an unstable equilibrium. So we want a stable equilibrium. So the idea that Arthur Askin gave is that to make a highest intensity point instead of highest intensity line, just put a high power lens in front of laser. So what lens do? A lens converts the light, and then there will be a point that is highest intensity. And if the lens is powerful enough, and then if we put the bead there, then the bead can't, even though the bead will feel the scattering force, but since there is a large gradient force, and the gradient force is larger than the scattering force, we will achieve this optical trapping. So in this case, particle can't go anywhere. It is moved in this three-dimensional space, and actually it has many application in our field, where we look at this tiny particles, and then we see the forces and we see the movements of tiny particles. So one application is this motor, kinesin motor. As in the last talk, Deepak showed you that these motors will walk on this microtubule. So and then with this optical tweezer, what we can do, we can make measurement of these things. We can make this we can just put a bead and we connect to the kinesin motor, and so here is this measurement. So you can see that this kinesin motor moves through this road, right? So this bead can actually measure the movement of this kinesin motor, this motor that is quite small, that works in our body. So you can see this this kinesin motor can take steps, small steps it takes in some time, it relaxes, and then at some time it takes steps, and then the position is increased. So position increased, it relaxes for some time, and then it takes another steps, it relaxes for some time, and then this motor takes another steps, and these quite small. So this is in nanometer range measurements, and that can be made using this setup, and this is quite simple setup. So at last I would like to demonstrate something that is some simulation thing. So what I will do, I will just show a Brownian particle that will just do Brownian motion in a water, and then I'll show that what if I turn on the trap, what can I do with that. So this is not my simulation. This is I taken from this FET, that is a website. Let's first turn off the laser. So laser is not here. The particle is only doing this Brownian motion, and Brownian motion every small particle will do because of this random kicks from the medium molecules. So, but if we want to control this particle, if we want to move this particle however we want, if we want to see that what the particle is feeling in this environment, small environment, we can't do it. But if I turn on the light, so if I turn on this laser light and then there is this lens, now the particle is trapped. Particle is trapped, it means that I can move the particle however I want in this small space, and it is quite nice because this particle is quite small. We can't see this particle, but we can control its position, and we can measure the forces in quite small ranges. So let me see this, show this in terms of this potential energy curve. So potential energy curves are just shows that where the particle wants to be. So lower this and lower this line, the particle will always want, or the system will always wants to be at that point, and system will try to reach a point of lowest energy. And then this lowest energy points depends on the power of the laser. So if I increase the power of the laser, this energy points actually goes down, which means now the particle is trapped even more with more power. So essentially the trap is acting as a spring, and if we increase the power intensity of the laser, it means that the stiffness of spring is increased.
Okay,
Yeah.
Let's thank Vaibhav for such an amazing talk.
Thank you.
One question.
So while in laser light, in blue cut lens, laser light will not travel.
Which lens? Sorry.
Blue cut lens.
She's saying that there's this lens introduced by the lens card, which, I mean, it's worn while using computers to block the blue light that's coming from the screen.
Yeah.
So she's asking how that works. Am I right? Yeah.
So for those lenses, actually lenses are made to in that case lenses are made up to clear your vision, and since the blue light is harmful for your eyes, so in that case I think they just put a coating on the glass so that only the light that passes through is of higher wavelength. So the coating will absorb or reflect the light of in this blue regime, and then only you can see the yellowish light part.
Yeah, let's thank him again.
But that lens will also make this. So in this case, the lens needs to be very powerful because the gradient force needs to be very large. But that lens also creates this converging lens. Yeah.
Okay.
And depends on the problem. Yeah.
So let's thank all the 4 speakers.